So, okay, let's start. So welcome everyone to the final webinar of upPE-T project. My name is Angela Gaetani. I'm the communications manager of the project. And today the title of our webinar is Upcycling Plastic Waste Packaging, Plastic Waste Packaging through Biotechnological Routes. Fuensanta Monzo is the coordinator of this Horizon project. And who will speak a little bit about the work that's been done so far before we hand it over to our presenters. We have 7 presenters for this morning. Before I hand it over to Fuensanta, just to let you know that the webinar is recorded and you have the option to raise your hands or ask any question in the chat box or after the presentations. There is a specific Q&A section after the first 3 presentations, but you will have the opportunity to ask any questions just after each presentation as well. So, Fuensanta, I'm handing it over to you.
Thank you, Angela, and thank you to all of you for joining this final upPE-T webinar. For those that don't know us, upPE-T is a project granted by the Horizon 2020 Research and Innovation Europe program with a consortium of 20 partners from 10 different European countries. We've been working for 4 years in finding new technologies and products more sustainable that can contribute to enabling the transition to a circular economy. Mainly we work on biotechnologies, different routes that make it possible the upcycling of waste of high concern and impact, which is the plastic packaging. We've been working, our technical partners have been working on developing new routes, enzymatic recycling routes, new ways of producing biodegradable plastics, and in new materials for biodegradable packaging. Today, they are showing you these relevant outcomes from the project that we are finalizing at the end of this month. So the floor is for our speakers.
So our first speaker is Soumya Kantidata. Soumya, if you would like to introduce yourself, and then you can start your presentation.
Yes, thank you, Angela. Thank you, Fuensanta. Let me share my screen with everyone. Entire screen. And I will start the presentation. Okay, I'm Soumya. I'm the CEO and founder of DigiTouch. And within the upPE-T project, DigiTouch is the work package leader of work package 7, in which we are looking after sustainability, valorization, as well as a lot of studying of policies, a lot of desk research around that, then also creating future standardization as well as the certification scheme. In addition to that, we are also leading work package 8, which is focused quite a lot on dissemination as well as exploitation of the key exploitable results and key outcomes of the upPE-T project. And in this presentation, I will talk a bit about the future certification scheme that we have developed together with the upPE-T partners. And so let me tell you in like very precise words where most of the value lies, why we had to create a new certification schemes and why we cannot use the existing ones. It's basically, we see that there is a gap in terms of certification when it comes to upcycled content. So we have a lot of standardization as well as certification that is done for recycled content that are used in plastic packaging that are we are commonly seeing in food and beverage packaging. But since upcycling is rather a new concept, the technology in upPE-T is also very innovative, very new. So we do not actually have a certification scheme around that, and this is one of the key, I think, um, contribution that we have created from the upPE-T project. So in my presentation, what I will say is that this proposed certification scheme, it combines the requirements of recycled content as well as biodegradability. So these two are very important. And as a result, it is then contributing to the development of biodegradable products in the context of, in a broader context of European circular economy. So that's where I think we have a clear value that the project upPE-T is bringing to the European community, which is around recyclability, upcycling, as well as circular economy. So if I start with the gap that I was saying in the sustainability landscape, so we see that we have a critical gap. So we are studying sustainability landscape for quite some time. We have established a framework, but our main focus here that we specifically want the certification scheme, its scope to be on upcycled plastic products with focus on food and beverage packaging, which is kind of the one of the main objectives of the upPE-T project. And this initiative aims to create a standardized approach for verifying upcycled content percentages. So we are quite clear in terms of what we want to do. So we want to verify, we want to say that, for example, when you see upcycled plastic, say in a plastic bottle or like food packaging. So if it says that it is 50% of upcycled content, we have similar certification for recycling, but not for upcycling. So that's where this initiative aims to go. And we also would like to certify the quality parameters in the plastic product. So this new certification scheme looks something like this, as you see in this picture. So it is based on, or rather it is encompassing several different parameters in terms of material composition, performance of the product, end-of-life sustainability. It also comes with a lot of pass and fail criteria, like what mandatory aspects you absolutely have to meet to pass all the checks to obtain the certification, and what if you don't do that, you sort of like fail for a certain for example, a certain criteria. Then we also looked into some of the relevant standards because it's necessary to be compliant with certain standards, and finally, it needs to be integrated with the European framework for sustainability and other things. So these were like some of our guiding principles behind creating this new certification scheme from upPE-T. Then I quickly go to the requirements because any product certification, whether it's software or hardware, that must have a set of requirements based on which we select the pass and fail criteria and other things. So in our case, we'd like to start with the upcycled plastic content. So this is the first and the foremost, like the very, very key point of that. So the product which we are certifying must contain a very favorable percentage of upcycled plastic. So this is one of our main thing. And how we can handle this verification, the process of verification, so that is kind of out of scope of the certification. So we kind of assume that we have a very favorable way of knowing the percentage. So if it is 50%, so it's 50%, if it is 60, it's 60, things like that. Then we move on to functional performance. For example, the product must meet or exceed functional performance requirements that we had set. It should have circular alignment with circular economy. For example, it should be recyclable in the end. Quality management, absolutely, the manufacturers must implement quality controls during production. We also have regulatory compliance. So if it is within the European market, so for example, meet all the European as well as international standards. And in some cases, for example, countries like France, they also have sometimes like some national regulations. So it should be meeting with those end consumer or like end market regulations as well. Moving on, then we define the scope of the certification, and I must say we have opted for a rather narrow scope rather than to have like a very broad scope of like aspects based on which the certification is provided. So you see like 5 key aspects that we have chosen. So we have the upcycled content focus. So this is very specifically to emphasize the use of upcycled aspects in the packaging. Yeah, so that's one of the key thing, and I always stress this fact when we are talking about this. Then the functional performance, we have then end product certification. So then regulatory alignment and exclusion of compostables. So we are very clear in stating like what is not in the scope of certification. So this is an important point to note. Then the key parameters and the pass levels. So we defined 7 key parameters. For example, upcycled content, feedstock purity, mechanical properties, barrier and shelf life performance, compostability or biodegradability, chemical safety, and upcycling process efficiency. The last one being optional, but it's kind of a recommended parameter. It depends on the authority which is providing certification. They may choose to make it like mandatory in future if they would like to. And for each of the parameter, we actually defined a pass level as a criteria to obtain the certificate. So for example, if we take upcycled content, so it can be defined as, okay, there has to be like at least 50% of the product by weight should be from the upcycled plastic waste, and it must be verifiable by like a traceability audit, for example, using digital product passport, for example. And if you do not have that, so rest of things doesn't make any sense, for example, because that's kind of our entry point to the certification. Then it can also, I mean, if you take the compostability or biodegradability in the consideration, so it must be complying with EN 13432, another or equivalent. So this is one of the existing standards that we have. So we have defined similar pass level criteria for rest of the parameters as well. Then moving on, this is how the methodology or the process of certification would work. So far we defined the scope, we defined the requirements, we defined the pass level criterion. But then if you see it from very, very high level perspective, how to obtain this certification. So we have this following methodology. So we have proposed that the certification should be issued with a 2-year validity. So this type of like duration is quite common in the industry. So 2-year might be, so depending on the context, it could be extended, it could be like even like limited a little bit, but I think it depends on the certification authority, how they would like to select it. So we put forward a proposal of 2 years, but definitely it's customizable. Then the company must continuously meet the certification criteria. So that's the ongoing compliance. Then we also proposed an annual audit for so as to trace the upgrade. If I go back here to trace the using digital product passport, the upcycled content percentage and other things. Then significant changes notification. So if there is a significant change in the process of manufacturing the upcycled product, it must inform the body or the national body which is providing the certification, because that might necessitate different type of audit for the certification. Then renewal audit in the end, it's conducted at the end of the period. So, for example, maybe if the certification time takes 1 month or 2 months, so from month 22 until month 24, then it can conduct another audit to renew the certification for 2 more years, for example. And definitely, we also recommend having a governance committee, which basically reviews the entire process of certification, checks all the pass level criteria and everything else is up to date. And they also ensure how the certification process and all the details should evolve as the market evolves in Europe towards more sustainability, climate neutral products. Then we also proposed a few steps beyond upPE-T because in our scope, we did not have this necessity of uh, creating the actual certification. So proposed we proposed 2 steps beyond the conclusion of the project upPE-T, so that this can actually be taken up by the industry or even the consortia of certification bodies. So at the short term, we think a successful pilot with the first certified upcycled product would be a major milestone. And this actually would give confidence in the mind of the industry in Europe that they can actually go through a set of defined processes to obtain the certification. And in the longer term, we think that the scheme should be taken up by independent certification bodies like CBS in Estonia or DI in Certo in Germany, for example, and should be recognized by the industry as well. Perhaps, having them mentioned in the purchase or procurement policies of the governments at the state level, or the national level, or even the European level. So that will significantly lower the barriers or like raise a lot of awareness for the upcycled plastics to enter the European market. And I would like to conclude with some proposed impacts and potential exploitation. So in case of upPE-T and in case of this work, so what we created is like a very structured solution to verify and showcase the sustainability credentials. So it's very, very important, as the European consumers have, or like they are trying to understand before purchasing the sustainability credentials of the products. So having those credentials for the plastic products emerging from innovative technologies like upPE-T will install a kind of like a trust in those products, in the new innovative technologies. I think that would be a major plus point for this. Then we should also look at encapsulating, the sustainability goals that we have in upPE-Ts, like zero, contributing towards zero waste, contributing towards more biodegradability, contributing towards very, very high percentage of recycled content. So they should serve as a key exploitable outcome that can potentially drive the market acceptance of upcycled plastic in Europe. So this certification could actually become an enabler of such sustainability goals when we present it in the form of a sustainability credential of the upcycled plastic product. And finally, it also responds to the societal needs to have like trustworthy levels. It again links to the sustainability credential point that I was mentioning at the beginning of the slide, that it can actually help consumers and businesses make like a lot of environmental friendly choice. And that's something we have as a need of the hour. So I think together this can actually enable a lot of short as well as long-term positive impacts to industries, to socially, in the mind of consumers, as well as for the governance at all the level. And if you'd like to have more information, so I would definitely draw your attention to the upPE-T website as well as our citizens engagement platform. So please visit that. And since the deliverable associated with this work is a public deliverable, so it would be uploaded into the upPE-T community of Xenor repository. So you'll be able to download it from there as well as consult it further. So going to details of the presentation that I just did. With that, I would say thank you very much, and I would give the floor back to Angela.
Thank you very much, Sumya. Because Sumya has to go earlier, I would suggest if any of the attendees have any questions, to raise their hands or to ask any questions to Sumia now. If there are any questions? No? Okay. Okay. So
I would leave, and thanks to everybody for having me. Okay, bye-bye.
thank you, Sumya. So if there are any questions, we will let you know. I'm sure that any of the other presenters can probably answer. Now Friedman Leopold from Enzymicals will talk about their work on enzymatic PET upcycling. Friedman, if you would like to say a little bit about yourself and your role in upPE-T, and then you can start your presentation. Thank you.
You are both muted, I think.
Friedman, we cannot hear you. You are muted. So you will have to start again. Thank you.
Can you hear me now?
Microphone is on. Yes, your microphone is on now. Thank you. You can start.
Sorry. My name is Friedemann Weipert. I'm a research scientist at Enzymicals, located in Greifswald, which is a university town at the northeast of Germany at the coast of the Baltic Sea. I have been working on developing novel petases and tailored the PET degradation towards the needs of the fermentation-based upcycling from the start of the upPE-T project. I would today like to give you an overview on enzymatic PET degradation and explain how Enzymicals is advancing enzymatic PET upcycling. Enzymicals has been established in 2009 as a spin-off from Professor Bomschuer's research group at the University of Greifswald. We have thus 15 years of experience in developing industrial biocatalysis, from the milligram to the ton scale. Over the course of that time, we have carried out contract research for clients from diverse industries, and thus we have built a large network of industrial partners. In particular, we have teamed up with other small and medium-sized companies in the biocatalysis sector to form the Enzyme Technology Alliance. These companies of this strategic alliance complement each other in terms of the technologies which they can offer. This way, we are combining our strengths to develop superior biocatalytic solutions. Enzymicals places a clear focus on contract research in white biotechnology. Our diverse team consists of 2 equal groups working on biological and chemical topics. They represent the necessary know-how in analytics, molecular biology, fermentation, biocatalysis, and process chemistry in order to fulfill our clients' needs for efficient biocatalytic solutions. We are thus able to offer expertise over the whole range of biocatalytic development, from initial biocatalyst identification to a proof of concept and further process optimization. I would now like to introduce you into the issues connected with plastic waste. As you all know, plastic plays a big role in our everyday lives. And polyethylene terephthalate, in short also PET, is a plastic commonly used in plastic bottles, food containers, and also fabric. Globally, over 70 million tons of PET are produced every year. And for sure, plastic has revolutionized our modern lives, but it comes with a hefty environmental price. As you can see on this scheme, unfortunately, only a small fraction of plastic is recycled, and most is discarded into the environment, goes to landfills or is incinerated. And you can see the effects of this on the picture on the right, where there's a beach completely littered up with plastic waste. This is not just an issue with macroscopic plastic, but also since plastic is and PET in particular is resistant to degradation in nature, it can persist for centuries in the environment. Also in forms of microplastics, which we have all heard of as an environmental issue. Of course, society is attempting to tackle these issues. And of course, one way to tackle this is recycling of plastic. There are currently two main routes to recycle plastics. The major route is still mechanical recycling, which means that the plastic is shredded into small pieces, melted, and reformed into new containers. However, this shortens the average length of the polymer chains and thus makes the plastic weaker, more brittle, and less useful. Consequently, the PET can usually only be recycled mechanically around 4 to 6 times. And so ultimately, even if it is recycled 4 to 6 times, it also ends up in landfills or incineration, where the material in the end is lost. To tackle this issue, an alternative is chemical recycling. This concept breaks the PET down into its initial building blocks, which are also called monomers. When the building blocks are later purified and repolymerized, we can generate PET with exactly the same quality as the virgin plastics. However, the downsides of this are that this process is very energy intensive and also often uses hazardous chemicals. So it's not particularly environmentally friendly. So, and now here comes an enzymatic solution. A few years, PETases, enzymes which degrade PET, have been found from some bacteria which grew on plastic waste. One of the first of these enzymes has been a PETase from Ideonella sacchaensis, but until now, over the last years, a lot of further PETases have been found and also industrially optimized. The concept of PETases is very much like in chemical recycling. The PETases act as a type of molecular scissors. So they cut the chain of the polyethylene terephthalate, which is made up out of terephthalic acid and ethylene glycol, which have been polymerized. They cut them into the building blocks, terephthalic acid and ethylene glycol. Much like in chemical recycling, just with a lot lower energy requirement and less hazardous chemicals. So on this basis, the concept of enzymatic recycling has been developed. Enzymes, the PETases, have got some requirements to degrade plastic. Mainly, it's very important that the PET is amorphous. You have to know there are amorphous and more crystalline forms of PET. You can see that when you also look at different types of packaging material. For example, you have more labile fruit packaging, like for strawberries, which is mainly amorphous. And on the other hand, you have more rigid packaging, for example, PET bottles, which are more semi-crystalline. And so in a first step, all of the more crystalline PET has to be amorphized. And there, pre-treatment techniques such as quenching, extrusion and quenching have been developed. Once the PET is amorphized, it can be mixed together with a PET degrading enzyme, the PETase, in a chemical reactor to carry out the depolymerization, very much like in chemical recycling, just under milder conditions. Now we are at a stage where we have the monomers, ethylene glycol and terephthalic acid. And there are now two different options. One option is to pursue a kind of enzymatic recycling. For this, you need to purify the monomers, and then they can be repolymerized. This strategy is, for example, followed by Carbios, a French company which is already developing and upscaling an industrial plant in eastern France in order to do chemical recycling of PET. This is certainly a very interesting concept. However, if you chemically or enzymatically recycle the PET, you still generate virgin PET again, which has the same properties of new PET and thus is also non-biodegradable. And if it ends up in the environment, you have the same issues of it persisting in the environment as with traditional PET. Our aim in upPE-T is a kind of different route. So we are using bacteria which can metabolize the monomers, ethylene glycol and terephthalic acid, in order to produce bioplastics, PHBV, which are biodegradable. Thus, we are upcycling the non-biodegradable PET to biodegradable PHBV, which creates additional value. I would now like to preview in particular what Enzymicus is doing in order to help proceed the upPE-T project. Our task was to tailor PETase biocatalysts in order to more efficiently break down the PET and also to enhance the PETase degradation process, focusing on practical temperatures and also focusing on the demands of the upcycling process for the later fermentation. So in a first step, we were looking at the biodiversity from nature, but also from databases in order to select novel PETases. Our aim was to find PETases which are both process stable and also feature at high temperatures and also feature a high activity for the degradation of polyethylene terephthalate. We selected a panel of PETases and cloned them first into E. coli in order to test whether they are true PETases and whether they are useful for further use in upPE-T. For this, we used first EPIs, an Eppendorf-style screening, and then also a parallel reactor system for further testing of these enzymes. The enzymes which seemed useful were further introduced into a cycle of optimization, where we looked at rational design, for example, optimizing positions close to substrate binding, but also loop engineering of these enzymes. From that, we achieved further optimized enzymes, which were then again tested in a parallel reactor system under different conditions like pH values, substrate loadings, and also temperatures. From that, the best set of enzymes emerged, which we used to further proceed to upscaling the enzyme production and to produce sufficient enzyme for a larger scale PET degradation. For upscaling the enzyme production, we also looked at alternative production hosts, such as Bacillus subtilis or Pichia pastoris. After we identified the most suitable production system, we optimized the enzyme production in a parallel fermenter unit. This allows us to test different fermentation conditions and media in a smaller scale of 1 to 2 liters in parallel for different conditions. The parallel fermenter units also very much mimics larger scale fermenters, which were then used to finally produce the PETase enzyme. On the other hand, we also worked on upscaling the PET degradation. There we tested different substrate loadings, reaction temperatures, also pH values, and also optimized the titrant and other conditions for optimal, in order to further optimize the conditions for further upcycling and the subsequent fermentation approach. Finally, we degraded the PET in a kilogram scale using 200 grams of PET per liter as substrate loading. In order to further optimize the PET degradation for the subsequent fermentation using Comamonas and Halopherax, we also tested whether it is possible to degrade the PET using the enzymes directly from the fermentation broth without breaking cells, without isolating any enzymes. This has got two advantages. Firstly, it saves us a lot of work to isolate the enzymes, and furthermore, the nutrients which come from the E. coli cultivation medium can also be used for cultivating the Comamonas and Halopherax in the end, which means that we are not wasting any material here, and we optimize the carbon efficiency. In order to further optimize our material, which we provide for the fermentation of Comamonas in the end, we also optimized the titrant, which is used to neutralize acid, which is released during the cleavage of polyethylene terephthalate. And we came up with ammonium hydroxide as an alternative titrant. This has the advantage that it also provides a nitrogen source for the subsequent Comamonas fermentation. So with all of our optimizations, we streamlined the PET degradation process, thus using the pre-treated PET waste and the enzyme which comes directly from a fermentation broth for the PET hydrolysis. And like that, we can keep all the nutrients and degradation processes, products for the microorganisms to produce biomass and PHBV. In the next presentation, Maria will show you how we modulated the further steps of this fermentation-based upcycling. And to summarize, we have shown that the enzymatic degradation of PET is certainly possible. And I have also introduced you into the different ways to upcycle the PET degradation products. One way would be the way to enzymatically recycle the PET. And our upPE-T way is to use the degradation process products in a fermentation-based process. I have shown you that enzymicals develop novel PETases, which we have also used for preparative PET degradation. And Enzymicals has also tailored the upscaling of the enzymatic PET degradation towards the requirements of the fermentation-based upcycling. I would like to thank you for your attention, and I'm later open for any questions. Thank you.
Thank you very much, Friedman. I don't know if people have any questions on Friedman's presentation. I can't see anything on in the chat box or in the Q&A section. There is a Q&A section at the bottom of Zoom. If people want to raise any questions or type anything in the comments. If not, we have a question for Mr. Tronch or Mrs. Don't know. Would you like to type the answer or answer live?
I cannot really see the question. Here, maybe. No.
You can.
I'm just looking at the chat, but I'm sorry, I cannot see the question.
There is a Q&A section at the bottom. Okay. This person is writing at the stage, so let's wait.
Pardon?
The person who is going to raise the question is typing. If you click, Friedman, if you click on Q&A at the bottom, in the bar at the bottom.
Okay, I see the person is saying I am writing. So
yes, so we will wait until the question is raised.
I mean, if the person needs more time to write, we can also continue with the next presentation, and I can reply after the next presentation.
Okay, let's wait for a few seconds and see, and so then we can act accordingly. Okay, as we wait for the question, we will come. Okay. Now, it says that regarding the production of PHBV from monomers, I also work with PETases and they require salts.
I would say that that very much depends on the specific PETase. There are examples of PETases which require quite a high concentration of salt. If you, for example, would look at the PHL7 or also known as PESH1, it requires something like 1 molar of sodium chloride in order to be efficient, to degrade PET efficiently, as far as I know it from the literature. On the other hand, if you would look at the LCC-ICCG, which would be the reference enzyme from Carbios, I believe that this can deal with much lower salt concentrations. And that is also our experience. So I would say it depends very much on the on the specific enzyme. So now there's a second question. Do you purify the monomers for the next fermentation? I think that's a very good question, and I think that's a big advantage of our upPET approach, because for the enzymatic recycling, which Carbios pursues, you definitely need to purify the monomers, otherwise you cannot repolymerize them. But as I showed you, for our upPET approach, our aim is to really use everything. The E. coli cell residues, the medium from the E. coli fermentation, and we put all of that into the cultivation of the Comamonas. So for the upPET concept, we do not need to purify the monomers, and that's a huge advantage of the upPET approach. Thank you for that question.
And there is a third question. LCC has lower performance in your experience compared to PHL7.
I think it very much depends on the reaction conditions. I personally don't have very much experience with PHL7, but what I can see from literature, it needs a lot of salt, which you need to add, which is not that much the case for LCC. So it probably depends a bit on the reaction conditions, but at lower salt concentrations, ICCG definitely has a higher performance than PHL7. And this has also been demonstrated in a review article, which was published around 1.5 years by Professor Bornscheuer and from the University of Greifswald and together with Carbios. But yes, we prefer to work at enzymicals. We prefer to work with enzymes which do not require these high salt concentrations, because it avoids us having to add additional chemicals. Does that
Thanks,
kind of
Friedman.
answer your question?
I can't see any other questions. I suggest we move to Mariana's presentation, and then we will have the opportunity for more questions after Mariana's presentation. So, Mariana, it's your turn.
Okay, can you see my screen?
Yes, you can.
Yes, perfect. Okay, so good morning. My name is Marianna Faraldi. I'm Chief Research Officer in Tecnoalimenti. Tecnoalimenti is a no-profit research organization. We are constituted as a consortium, industry-driven. Indeed, we are constituted by 31 shareholders represented by Italian food processors. So as you can imagine, the interest for us is in particular in the application in real conditions of this new solution developed in upPET project. This is the picture which represents all the steps of upPET, and as you can imagine, we have been mainly involved in the new upPET food and drink biopackaging development, but in particular validation. So Tecnoalimenti has been into the project the leader of the validation phase. According to this industrial interest, we have been allocated also as exploitation manager. So my presentation will be mainly focused on the validation phase, but I would like just to spend some words on the overall process develop into upPET. So as you understood, polyhydroxyalkanoates are polyesters typically obtained from fermentation using different bacterial strains and carbon sources. So this is a premise which has to be done. So to date, as consumers, you know that on your tables in your kitchen, you do not have any food packaging made by PHA. And there is a main reason that is that to date this kind of bioplastic is relatively high cost compared to the other fossil-based solutions. Obviously, this represents the main limitation underlying the further expansion of PHA in the market. Therefore, strong efforts are currently targeted on searching for novel trends in the biotechnological production of PHA that would increase the economical feasibility and competitiveness of PHA uses. So Friedman, before in the previous presentation, focused indeed on all this part. So what has been demonstrated is that in the biotechnological route, in particular in the second part, so in the part which starts from the obtainment of the sources which need to be included into the fermentation reactor, we noticed that 40% of the final cost of PHA derives from the cost of the carbon source. Therefore, there are attempts to omit expensive carbon substrates, in particular pure carbon substrates as such, but utilize cheap, abundant, and human food chain non-competing resources such as waste streams of agriculture or food industry, which can be very, very, very useful indeed for decreasing these costs and help the finalization of the overall process. So the strategy which upPE-T developed is indeed valorizing this waste as feedstock for the biotechnological process and the bioproduction of these polyhydroxyalkanoates in a sustainable and competitive way. So what we try to stress is indeed that a new value can be obtained from the waste from the agri-food sector. So we demonstrated that we can start from the waste from this important sector. And so, for example, as my colleagues will present later on, we used a lot the sugar rich food industry waste represented by the candy industry waste, but we started also from the post-consumption PET bottles. So as you can imagine, we don't start only from the agri-food waste per se, only on the organic, I would say, substances, but we have this holistic vision, and so we can start also from the bottles, from something which is, in any case, related to the food consumption per se. So this part will be better presented later on by my colleagues. So I will try to go quick in this part. So as Friedman already said, the first step, the first process step is represented by this PET enzymatic degradation for obtaining these monomers, so terephthalic acid and ethylene glycol, who represent the starting point for a further process through Comomonas testosterone and Allopherax mediterraneae bacteria for obtaining these biomass and from which extracting the PHBV. But the second process step on which I want to focus is the compounding phase. So we obtain this PHBV and we had some additives which will provide the right characteristics to to the polymers which we want to obtain for the next steps, and blending with other kind of bioplastics, we will obtain at the very end these pellets, which can be submitted to further transformation into rigid, semi-rigid, or flexible packaging solutions. So along the upPE-T project, we tested different kind of processing possibilities: injection molding for obtaining sticks, thermoforming for obtaining trays, and blown and cast extrusion for obtaining flexible films, and so under the form of reels. So as you can imagine, all these kind of prototypes are fundamental in the food industry everyday activity. So the third process step was represented by the industrial validation. So once this prototype were ready, it was fundamental to test in real industrial conditions. So we involved the real food industry, and for testing processability, mechanical barrier, and thermal properties of these new solutions. So making a step behind, what is the industrial interest in this new material? So as you can imagine, this material is characterized by more sustainability compared to fossil-based materials in terms of environmental impact. So in this famous picture provided by European Bioplastics, you can see as PHA is put on the right and characterized as a biodegradable and bio-based polymer. So this is fundamental for the food industry in a future vision for being more sustainable. And I would like to add that PHA not only can be biodegradable and bio-based, but can be also recyclable. Indeed, this is something which we tested along upPE-T project. So all these three characteristics make this new solution very appealing for a food industry, for being indeed more close to the new law in this direction, but also close to the consumer's request in this sense. But the second important industrial interest in this new material is to demonstrate the performances and products' shelf life, which are more or less comparable to the petrochemical plastic currently used. So obviously the industrial interest is to demonstrate that this new solution is on one side green, but on the other side comparable from the industrial point of view to the solutions which are currently in place. In this table, you can see from literature that it was underlined as PHA and PHA blends can be good potential bio-based alternatives to petrochemical plastics such as polyethylene and polypropylene. So those type of plastics which currently are commonly used by the food industry in Europe and outside. So what is important to demonstrate is the processability of the new material. So to demonstrate that it runs through industrial machine. So for a food industry, it is important to demonstrate that they have not to invest in new industrial machines, but to demonstrate that the current ones are fine as well, or really small modifications are needed. Another important point is the comparable performances in terms of resistance at the break, at the temperature, at the stress, the flexibility. So these are characteristics which need absolutely to be tested and validated. On the other side, the most important I would say function of the food packaging is for sure the preservation of the food inside. So the industrial companies need to guarantee that the food is safe from the moment of the production until the expiry date, and that the quality is not changed for any reason. In this sense, it is fundamental to demonstrate the weldability of the food packaging, so that it is sealable, and so everything inside is in some way protected from the environment, but also that along the shelf life, no off flavors are developed to maintain the sensory properties and avoid the growth of unwanted microorganisms and molds. So we tested upPE-T solution in 4 industrial sectors with different kind of needs. So the meat, the dairy, the bakery, and the candies. Because obviously, as you know, each sector and each specific food product has specific needs and requirements. So we wanted to diversify the validation phase for having a lot of evidences and information for the further exploitation of our results. So the flexible films have been developed by Biomi in Croatia, and these flexible films have been tested together with the sticks developed by Moses in Spain by Durukan, who is an industrial partner in Turkey. And they develop candies. So the use case we selected is the lollipop. So it was very important for them to test, for example, the flexibility, but also the characteristic of the sticks and the capability of the envelope to be adherent to the candy. On the other side, in the meat industry, we have Villani Salumi, who is an Italian company in the north of Italy. And we tested together the compatibility of the trays developed by Moses, so this more semi-rigid packaging solution, together with the top with flexible film. And as you can imagine, here the challenge was in particular the capability and the compatibility of both parts. For the bakery industry, we decided to test the flow pack mechanism. So for those who are not familiar with this concept, this is very, very typical in the food industry, and it is an automatic machine for high productivity horizontal packaging, which uses a single reel of film to create the packaging with 3 seals, 2 transversal and 1 longitudinal. So it is very, very typical for the bakery sector and biscuits and croissant and this kind of products. The last but not least test has been done in the dairy industry, and also in this case we tested only the flexible single reel in industrial machine, which is able to pack this specific cheese with a tomino, and who is very particular because it has to be cooked for consumption, but in particular needs a particular type of packaging because it has to be breathable. So differently from other kind of products, it needs to have the possibility to be breathable along the shelf life period. As I said, the weldability test was very, very important for different reasons. It has been tested in all the sectors. And the most challenging, as I said, was represented by the meat sector because it had to test this match between the tray and the flexible film. In any case, we can say that the trial was successful because it was demonstrated that it is feasible. We had some problems. As you can imagine, it is a research project, so obviously we are experimenting something which can be improved more in the future. We noticed, for example, through residual oxygen testing that even if from a visual appearance the compatibility was 100% fine, we noticed that with our test there was some oxygen inside, so demonstrating that probably this sealing was not perfect. But obviously we can still work more on this in this regard. What I want also to stress is that obviously, since this is a new material for a food industry, it is important to set up all the conditions, so the pressure for the sealing, the temperature, and obviously it is not everything clear. Everything has to be tested, and different kind of trials are needed for understanding what are the optimal conditions for obtaining the optimal final result. But what is important is to demonstrate that at the very end it is feasible. And this is what happened, for example, also for the lollipop. So after some problems, some breaks, at the very end, it was demonstrated that at specific conditions, it was fine. Indeed, as you can see, this prototype is very, very nice. The flow pack mechanism was successful, so it works without specific problems along the trial from the mechanical and processing point of view. And also in the case of the Tomino, it worked properly. So it was possible to cut in proper way the flexible film and to pack properly. And also the label is fine and well adherent to the packaging. Once these samples have been created, we moved to the shelf life analysis. So as I said, it is important to test the sensorial and microbiological aspect in this regard. These products have different needs, requirements, and challenges or risks which can occur along the shelf life. Boku, who is located in Austria, supported us in this shelf life analysis. Summarizing, we can say that the lollies took up a small amount of water during storage, but never reaching a sticky or slippery status, so a good result. The cheese also does good, so for this specific cheese, who has this specific breathability needs, this kind of new material is very good. Some problems which have to be eventually faced in the future about weight loss of the food product along the shelf life. No contamination growing on the surface and pH values in the range. Biscuits also did quite well. Indeed, the water absorption was less than predicted. As you can imagine, the meat performed in a different way because the challenges related to this fresh product are different from the others. Indeed, it had discoloring and flour changed very quickly, and some random contamination was there. So the conclusions of this experience and the lessons learned. So to date, we can affirm that a new material based on PHB, 30% hydroxyvalerate, can be a possible substitute to polypropylene or polyethylene. Indeed, we demonstrated the possibility to use the same industrial plants currently used for thermoplastics. There is a good compatibility with existing food industrial packaging machines, a good handling, sealing capability, rolling up capability, and quite good film resistance tested also in industrial conditions. We tested so far thicknesses around 40-60 microns. But as you know, the current solutions on the market are around 30 microns. But for sure, there is some space for improving. In terms of shelf life studies, we perform both sensorial and microbiological tests. And the results were promising in the case of lollipops, bakery, and dairy sectors, while some issues still need to be solved for meat, being the product more sensitive to water vapor and oxygen. So we can summarize saying that PHBV-based material can represent a future alternative to fossil-based biopolymers in food packaging in those sectors where barrier properties are not particularly restrictive or where the higher water vapor permeability is of advantage, as in the case of our selected cheese, Tomino, but also very good, for example, for fresh fruits or vegetables. We have not tested here, but in other projects, and this is quite clear. Is the material ready for the market? Not yet. There are still some challenges. So for sure, as I said, if we want to enlarge the sectors for applications, we need to improve the mechanical and barrier properties more. This could be done through functionalization or lamination, for example. There is also a problem of costs, which is still too high for the food industry. So this is something which is important for industrial partners for moving in this transition towards these bioplastic new solutions. The production capacity, currently it is too low, so there are not enough lack of investments. We analyze this and we notice that few investments because the market is not demanding so much. But on the other side, obviously, if it could change, so if the law moves in this direction or the consumer asks, for sure, the market demand can increase and also the production capability according to new investments. The raw material choice, so the feedstock is very important because as I mentioned at the very beginning of this presentation, it can affect the production costs and also the LCA. In a previous project, we demonstrated that if the raw material selected as another kind of route, and this can impact a lot the LCA analysis. And last but not least, it is important to work on the waste management at the municipal level because it is very important that at the domestic level, people understand the correct management of waste separation, and it is not clear enough at the moment. Thank you.
Thanks, Mariana, for your presentation, which was really nice and informative. It's time for questions at this stage, and then we will have a few minutes coffee break. Another question regarding to the production capacity, are yields acceptable?
So if you are asking at the industrial level, I would say that we had 50% of waste in this moment. So we are in research environment. So as I said, the setting is not yet finalized. So more or less, we had 50% of waste compared to the material at the very beginning and the final. If you are asking about the PHBV production, I think that my colleagues in the future presentations will be more precise in this regard.
Vincent also wants to comment probably on this.
Yes, to Friedemann, they have developed a new enzyme, a novel enzyme. What is the features of this new enzyme compared to the existing ones in currently existing ones?
So thank you for that question. I think we can say that we have developed very good pipetteases which are suitable for preparative PET degradation and which perform in a similar range to the reference enzyme LCC. Does that answer
Okay.
your question?
Yes.
Are there any questions from people for any of the presentations, the first three? Okay, I suggest we have a 10-minute break until 11:30, and then we will come back for the next 4 presentations before we close the webinar. See you in a bit. See you in 10 minutes.
See.
Now we are continuing our webinar with the presentation of Alejandro Arribas. So the floor is yours, Alejandro. Just say a few words about your role and then you can start your presentation. Thank you.
Thank you, Angela. I'm going to share my screen. You see my screen?
Yes, we can.
So, my name is Alejandro Rivas, and I work at the Research and Development Department of CETEC. In the upPE-T project, I am the work package leader for work package 5, which is related to the compounding and transformation of the PHPV into packaging and full contact applications. This is a short index that we are going to talk about how this we can scale the extrusion process from the lab to the a small pilot plant. First of all, what is the many of you know the upPE-T project. One of the case of the upPE-T project is to produce PHPV polymer through biotechnological process using the microorganism Alpheras mediterranae. And following biomass production, the polymer is extracted via solvent process, and subsequently the PHPV undergoes extrusion to create blends with other polyesters such as PLA and PDS. This process is initiated at laboratory scale, involving a few grams, and then it is scaled up to a pilot plant, processing a few kilograms. The final objective is to produce polyester blends for flexible and rigid packaging. What is the extrusion process? The extrusion process is a technology in the polymer processing industry, and it is broadly used for the production of pipe and profiles, but also many films and sheets, and for specialty operations such as blend compounding. The extrusion process is not only used in the plastic sector, but also in metal and food processing industries, but their use is particularly prevalent in product manufacturing that uses polymers as raw material. Major extruders are classified as single screw or twin screw extruders, with single screw extruders widely applied for general polymer processing and twin screw extruders used for compounding polymer blends. Twin screw extruders can be further divided into intermeshing and non-intermeshing types. And in the upPE-T project, we use single screw and twin screw extruders. The single screw extruders were used to produce films, and the tune screw extruders were used to obtain blends of PHBD with PLA and PBS. In this presentation, we'll talk a little about tune screw extruders and how we work to scale blends of a few grams to blends weighing several kilograms. What is the extruder and how it works? Basically, the extruder consists of a heated chamber or barrel containing a warm screw driven by a motor. The plastic is introduced through the feed zone and the screw advances the plastic. The plastic melts due to the chamber temperature and it is forced out through an orifice. The resulting strand is cooled in a water bath, for example, and finally it is cut to obtain pellets. The extruder screw is divided into three sections: the feed zone, the compression zone, and the metering section. Each section is designed to sweep the polymer and achieve specific effects, such as additive dispersion or blend homogenization. The L-to-D ratio between is the relation between the length and the diameter of an extruded screw, and this relation it's a crucial parameter in the design and operation of an extruder because it significantly impacts the processing of polymers. And how this LD ratio affects extrusion? Regarding the mixing and melting, a higher LD ratio generally provides better mixing and melting of the polymer. And this is because the material spends more time within the extruder, allowing for more through heat transfer and sharing. And conversely, a lower LD ratio may result in less uniform melting and mixing. Regarding the output and pressure, the LD ratio can also influence the output rate and the pressure generated within the extruder. Longer screws tend to generate higher pressures, and regarding material processing, the optimal LD ratio varies depending on the type of the polymer that is being processed. Some polymers require longer screws for adequate melting and mixing, while others may be processed in a good way with shorter screws. But in summary, the LD ratio is a critical factor in extruder design, influencing mixing, melting, output, and pressure. The appropriate ratio depends heavily on the polymer being processed and the desired outcome. Here on the left, you can see our microcompounder designed for small batch mixes of a few grams. And on the right, our pilot plant extruder that enable us to process up to 10 kilograms per hour. And now I'm going to explain how they works. The microcompounder, it's dividing in, we can control the temperature in six zones. It can be heated and cooled quickly in intervals of 10 to 15 minutes. We can work with very small volumes between 2 and 15 millimeters, that it's equivalent to 10 to 20 grams. The screws are fully meshed, and we can increase the LD ratio or improving mixing, simulating by increasing the recirculation time using a valve at the bottom of the device. Here with more detail, a high shear rate zone is present at the top of the screw, and the shear gradually decreases as the material moves along the lower part of the screws. We can increase the LD ratio by recirculating the material through the recirculation channel. And once the mixture is homogeneous, we close the recirculation channel and remove the material through the die opening. What happens when we move to a bigger scale? We have taken into account several key variables that come into play. First, the polymer's inherent properties, particularly its thermal behavior, that it is paramount. Understanding its melting point and thermal stability, it's essential for setting the appropriate processing temperatures. Secondly, the design and rotational speed of the extruder screw directly influence the shear forces applied to the polymer. These forces affect the polymer's melt flow, mixing, and ultimately the final product's properties. Lastly, consistent throughput and feeding are critical for uniform processing. Variations in feed rate can lead to inconsistencies in melt quality and product dimensions. How to reduce the additive agglomerates such as small polymer portions? That is, it should provide the dispersive mixing on the left figure. Once the small polymer portions have been broken up, then an uniform distribution, that is a random spatial orientation of the dispersed polymer, is required. This is known as distributive mixing. The two mixing processes are not totally separated. When dispersive mixing is performed, there always is some distribution mixing, but the converse is not always true. And what does all this depend on? The polymer must be processed above its glass transition temperature, but below its degradation temperature. The blend also should be processed above its melting temperature in case of the polymer have some degree of crystallinity, and also the temperature influences the melt's viscosity. A low temperature results in high melt viscosity and high torque. An elevated temperature reduces the torque due to lower melt viscosity, but it increases the risk of polymer degradation. The temperature of the blend will differ from the barrel temperature due to mechanical energy transfer from the screws to the molten material. In single screw hot melt extrusions, temperature mainly affect the flow rate, as a polymer's flow properties are proportional to its viscosity. When you increase the barrel temperature in single screw extruders, you increase the filling rate, but decreases the residence time of the product in the barrel. The barrel temperature also influences the residence time in twin screw extrusion. In twin screw extruders, the throughput has significant influence on the residence time. A higher throughput decreases the main residence time and the weight of residence time distribution. The influence of the screw speed on the residence time is rather low, and backward mixing elements have a high impact on the residence time and distribution increases. The main effect of the melt temperature comes from the screw speed and feed rate. That means that a higher melt temperature is measured due to mechanical energy input in the mixing zones at higher screw speeds. Finally, you can see here how we get with the homogenization process in the twin screw extruder. The strand exciting the extruder is cut by a pelletizer, producing pellets. The pellets you can see on the right. This is the PHPV final aspect of the pellets. However, to assess the degree of homogenization, we must analyze these pellets. How analyze this pellet? With a scanning electronic microscope, we can see several pictures from several blends with different PLA and PHPV ratios, and you can see how the two phases are dispersed within each other. Good dispersion and homogenization of the two polymer phases is observed in all cases. And finally, here the products developed with the flexible and rigid blends from the upPE-T projects, and specifically on the left you can see the lollipops sticks made with PHPV PDS blend, and on the right trays made with PHPV and PLA. But from here to this is another history that our colleague Mariana have said before. So thank you very much, and if you have any questions.
Thank you, Alejandro. Let's see if there are any questions in the Q&A box. Just to let everyone know that there is going to be
a very technical presentation, maybe, I think.
Yeah. Yeah, probably this is the reason. Okay, we can move on to the next presentation from Fernanda about the business plan. Fernanda, you can say a little bit about yourself and then you can start your presentation. Thanks.
Yes, here. Hello, can you hear me?
Yes, we can.
Perfect. Well, hello everyone. My name is Fernanda da Costa. I'm a business developer in DigiTouch. I have over 8 years of experience in marketing and business development. And my experience relies on R&D companies focused on mobility and sustainability, where I'm mostly working with emerging technology. I have been working with upPE-T for the last year, taking charge of the development of the first pre-commercial business plan for upPE-T. And today I will present to you the methodology on a high level analysis on how we decided the business plan for this emerging technology. So can you see my screen? Sorry.
Yes.
Mm-hmm. Okay, great. So let's get started. So let me talk about our taking upPE-T. So this project has been going for 4 years. So as you can imagine, there have been several key exploitable results that we had discovered. However, in this case, for the business plan, we need to identify those KER that have a commercial potential and that have been viable. The two that we have identified are these ones, the pretreatment process for PET waste degradation to facilitate enzymatic attack, and the enzymatic upcycling of the polymer and production of PHBV. So this is the case for upPE-T, but for other technologies, you can identify as many as you can justify. Yeah. So when you're creating a business plan, this requires to have a clearly understanding of the problem and the solution. So here, collaboration was essential. The feedback from all the partners was really helpful. And also, this is a new industry, so we can face limited complex data that is available on the websites and reports. So we have to rely mostly on secondary research for this market insights. To compensate this research, we held workshops to gather insights from each partners and their experiences. I mean, as you see, we have all the different types of experts in our team. And well, this will lead productive brainstorming sessions. We use different tools, right? Online tools and other type of tools that I am going to share with you in the following slides that helped us visualize the technology workflow and the approach that we wanted to take. And as part of an initiative from the European Commission, we applied to the Horizon Result Booster, which is a tool that aimed to enhance the market impact of publicly funded EU research. And this is helping us to address challenges by helping the business, the business plan for the different KER that we had identified through training and expert support. So the HRB services was very important for us to confirm that our approach was pointing out the factors that we were missing. So we organize our business planning through 3 different sections of ideation, development, and go-to-market. Each section has a specific part. So for the ideation section, we will explain the technology a little bit more, but not in a technical point of view. We have to identify the problems and the solutions that we are going to offer with our solution. And all this is going to be projected into the value proposition by using a tool that it's called the business model canvas. In the development section, we will analyze external factors that will affect the project and the technology in the market that is using different tools and other types of analysis. And finally, the go-to-market section. So here we will use all the information that we have gathered from our value proposition and our analysis to create a market entry strategy. This will include the description of the business model, the financial projection, the risk assessment and mitigation, and the exploitable map. So as mentioned, during the ideation phase, we need to identify the problems addressed and the proposed solutions. In this case, it's important to understand the issues across different spheres. So the spheres that I considered important was the economic, the integration, the environmental impact, and focus. Now, one thing that it's crucial to highlight is that during this phase where you are addressing different problems, you have to ask as many questions as you think that are necessary. There is never enough. And well, here are some questions that I thought of. So it's, for instance, for the economic part, is it a cost-saving solution? How will this impact the current CAPEX future clients, and so on? Integration. Is it easy for current clients to integrate this technology into the existing practices? How compatible it is with the client's current infrastructure? The environmental impact. In what ways the solution is environmental friendly? And this will be more explained mostly in the LCA studies, but also you have to have that clear for what you are offering, right? Is this process, is it in the process, the resources, or the outcome? Yeah. And the focus, what are the client's current priorities? Everything has to be very customer-centered. Once that we have identified the problems that we need that are needed to be addressed, we have to begin mapping. Now, I'm a very visual person. Everyone has a different way of how to organize it, but this is something that I highly recommend. I use this tool that probably most of you know about. It's the business model canvas, where you can use it to outline visually the different elements. And these elements are customer segments, value propositions, channels, customer relationships, revenue streams, key resources, key activities, key partners, and cost structure. So this is how the chart looks. If you see in each box, you're going to find like some questions. These are not the only questions. Again, questioning is never stopping. So you have to keep on asking as many questions as you want. And also, in this case, as I mentioned, we have identified 2 key Rs. So you have to create a business model canvas for each of them. In case you have found more for a different other technology, you have found more than 1 key ER, you have to prepare BMC for each of them. And another thing, again, collaboration is key. So you can answer most of these questions on your own, but it's going to give you better insights if you use help from your other experts that you have available. Yeah, for the development section, we use different tools. In this case, there were 4. There were the PESTEL analysis, the market analysis, the SWOT analysis, and competitors analysis, which I'm going to explain a little bit more in detail in the following slides. So as much as we want to commercialize our solution globally, we need to start from one point. Therefore, we must identify the countries that show the potential, like the potential interest in adopting our technology. So PESTEL stands for political, economical, social, technological, environmental, and legal. These are the different factors that we are analyzing with this tool. And we need these factors to understand how it is going to make the influence into the market opportunities. So for upPE-T, we consider the countries with the largest capacity for further PET processing and pelletization via extrusion. Why is this? Because we understand that these countries, the top countries, are the ones that have a better infrastructure and accessible technology for the processing of the PET. So we have already identified our countries. So in this case, we are counting the first 4. And we start to do research on all these factors, of all the vessel factors. And once that we have already done this, we have to assess, we have to go further to this analysis and assess the best options based on the criteria and evaluate the countries accordingly. So the criteria that we chose was the regulatory environment, the research subsidiaries, tax advantages of each country, the labor costs, location benefits, political stability, technological advancements, and language barriers. Yeah. For the market analysis, in this section, we are analyzing the market through using 3 different concepts: TAM, SAM, and SUM. So TAM stands for total addressable market. It includes all potential market demand. SAM, or serviceable addressable market, refers to the part of the market that we can based on the geography, which was the winner from our vessel analysis, yeah? And SUM, or serviceable obtainable market, is the realistic share of the market that we can capture. So like the business model canvas, we need to apply the same type of analysis. It's one per each KER that we have identified. In this case, I'm going to tell you an example how we got the TAM, SAM, SUM for the first KER. So for TAM, I define it as the total amount and growth rate of plastic production and the policy drive in Europe. For SAM, since we have identified Germany and France, the 2 main countries where we are going to be studying and working, we started to do a deeper research on the waste collection, the extrusion capacity, and the sorting infrastructure of Germany and France. And SUM, we did another analysis to identify which are the key players in the PET recycling industry in Germany and France. So which are the potential customers that might be interested in this specific technology. Another tool that we used was the SWOT analysis. It's another common tool, but it's really useful when you know how to apply it. So SWOT, for the ones that doesn't know, it stands for strengths, weaknesses, opportunities, and threats. What it helps us to assess both internal and external factors that can affect the project positively and negatively. So it's not the matter of making a list of the strengths and weaknesses of your technologies and opportunities and threats from the market, but once that you have already gathered this specific list, you have to do a deeper analysis into understanding how is it going to affect each other. So we do a cross mapping, all of these points, and the different way how we are going to get a comprehensive strategy for this. So some of the questions that you're going to ask yourself is like, what are the strengths that are aligned with the market opportunities? The mitigation of the potential threats with our strengths. How are we addressing the weaknesses by embracing the opportunities that are being shown? And finally, how are we mitigating the risks where weaknesses intersect with threats? And this, by analyzing this information, we gain not only an assessment of the factors, but also valuable insight that will help us to develop future strategies. For the competitors analysis, we need to identify the competitors' strengths and weaknesses from different angles. When we are selling an IP of the technology, we need to identify the perception of the final outcome of this technology and how it would be perceived by clients that will apply the technology, that, like for instance, the retailers and of course the final customers. We need to understand the attributes that are important for each player, and in the case of a material outcome as how it is ours, evaluate the mechanical, chemical, and environmental properties that each stakeholder will value. And and what about the direct and indirect competitors of the technology? Like, how do you know that the final outcome of your technology cannot be done better using another technology? We need to identify that as well. For upPE-T, we consider two different competitors analysis: the plastic and bioplastic manufacturers and the recycling methods and technologies. So these are mechanical, chemical, and enzymatic types of technologies. So effective competitor analysis in tech development, it requires looking beyond the market share. So we have to dig deeper into the perception, the performance, and the potential disruption of our technology. Now, for the go-to-market section, we will discuss about the business model that we had chosen for the technology, the methodology behind the financial projections, the exploitation map, and the risk assessment done. As mentioned before, the primary value relies on the IP, the intellectual property, and it can be customized for the client's for the current client's technology. The best type of model to follow in these cases is licensing. But how can we offer licensing for an early stage of technology? Well, one way is by offering non-exclusive licensing. This will increase the revenue streams, prevent us from depending on a single license, and also accelerate the market penetration. Then we need to consider also the license scope and the applications permitted for the produce. So for upPE-T, we will be limited for the European continent and for the production of different types of PHB, like the rigid, semi-rigid, and flexible plastic. Also, how are these different types of plastic going to be reproduced for? Is it going to be for food and consumers goods packaging? Maybe in the future is going to evolve for going to medical applications or agricultural applications. So, but for now, it's just food and consumer goods package. Since we need to maximize both short and long-term, short-term revenue and long-term potential, while retaining the flexibility to capitalize on future demand of other markets, we need to have a phased approach. This refers to the technology's maturity in the long and short term. So in this case, we have the pilot testing license for the short term, which is a license of 1 year for testing and for validation phase. And also, since the long-term part, the long-term phase or the commercial license would be full term, and this is going to be customized. For the upfront license fee, we will be a one-time payment for access to technology, and it will be customized according, again, to the client's objectives and needs, and the region and application. And this will fee be adapted by these two. Then the royalties will be based on a tier type system according to the pilot testing license and the commercial licensing. For the commercial licensing and royal fee option, will be presented according to the percentage of revenue. And also we cannot never forget the partnerships, like we have the partnerships with public and private grants, with private companies and other R&Ds. So when talking about financial projections for the corporate finance analysis remains on the testing phase, and it relies on a series of careful considered assumptions. These assumptions made for financial modeling purposes can go with production capacity, sales, the useful life of equipment, electricity costs, factory size, rent, and so on. And the variables such as production costs, market prices, and operational expenses are based on preliminary data and industry benchmarks, serving as a model to guide future planning. This also has to be depending the region where you have chosen. In this case, was either Germany or France. And finally, as the project progresses, more data is going to become available. So these financial projections will keep on being refined to reflect real-world performance. When developing an exploitation plan, and the strategy for transitioning towards commercial maturity, we must assess various actions related to technical aspects, including the requirements and challenges that may appear, the regulation requirements to ensure compliance and legal standards, and commercialization when developing commercial strategies and partnerships, and what kind of partnerships that can align with the business model that we have planned to implement. This strategy has been done for the years 0, 3, and 5 after the project's conclusion in preparation for the business commercial launch. So once that we have covered all the information and crafted an initial strategy to introduce our solution, we need to identify the associated risks and their mitigation measures. The key areas to consider are regulatory risks, where we should review the compliance challenges and legal uncertainties that we can face in the future. Financial risks, this involves identifying potential financial challenges and their impacts on development and continuity of the project. The commercial risks, these relate to business performance, such as market perception or acceptance of our technology. And technological risks, where we must consider issues related to any technology, to the technology risk related. So these are including undesired results or complications that may arise during the scaling up. By addressing these areas, we can better prepare for potential obstacles as we move forward. So yeah, finally, as a conclusion, well, when we are developing a business plan for emerging technologies, we have to leverage in a wide range of resources, all different types of resources that you have access to, and also the insights of your partners. As mentioned, and I repeat, collaboration is key. So the partners' insights and expertise you must not underestimate. There is no one size fits all. There is not a written formula to writing a business plan, as this is a technology that is in constant change. So each technology presents their challenges and priorities. So you should be flexible enough to understand how to take the approach on that. And it's not set in stone, so it's keep on changing. So you may do the adjustments as how you go. And while there are countless types of tools, I just share some of the ones that we've used, but you can find other many tools that are available. So select a few, but do be mindful of the ones that are going to give you a deep insight of what you need. So choose wisely. And that's all from my side. Thank you so much. I don't know if there are any questions.
Thank you, Fernanda. There is one question in the Q&A box. Are you going to patent the microorganism for PHPV production? I mean, a wild type strain was used or was genetically modified to boost conversation yield or whatever, therefore it can be industrially protected. I think this is relevant.
Yeah.
Many thanks, Natas.
Thank you. Thank you so much, Marta. Yeah, so for the patenting, for now, we're not introducing the patenting. We are doing some research on the certifications, but patenting might take more time as we are going to be needed some legal feedback, some legal expertise that might be involved. So in the time, it's not going to be done. Second question was strain was used or was
genetically modified to boost conversation.
Yeah, I mean, for whatever it is, for the protection of the different levels of the technology, that's something that also has to be studied by both the experts and also the legal team. So it's a joint collaboration in this case, but for sure it's something that had been addressed, and it had been also considered and also written down in the business plan for the potential of having already a patent by the year 3. So yeah. Thank you.
When Santa wants to also comment.
Yes, well, together with the business plan, we have elaborated the exploitation plan, where all these ways of protecting the different new innovations have been evaluated, and a route have been decided for each new innovation in the project.
Great, thank you. Are there any other questions from people? No? We're very good in terms of time. So I will then hand over to Maria Ailo.
Can you hear me?
Yes, we can. If you could just say a few words about yourself and your role in upPE-T, and then you can start your presentation. Thank you.
Yeah, can you see my screen also?
Yes, we can.
Good. So, good morning, everyone. I am Maria Aiello, and I am a sustainability expert in Digitouch. My role in upPE-T is to assess and prove the overall sustainability of the upPE-T products, which is the PHBB. And in this presentation, I am going through the sustainability challenges and the valorization opportunities that we faced specifically during these 3 years that I have been working into the project. So first of all, I want to, it's not changing. Sorry, I'm having some problem with my computer. Okay. So first of all, I want to state the problem, let's say, that we are now facing with the plastic waste. So you know that plastic is a very wide used material for a lot of purpose, such as packaging or anything that can be basically used one single use. For this reason, there is also a problem in the waste management of plastic. First of all, yes, it is possible to recycle it, but when it is not recycled, it is landfilled or incinerated, and this generates relevant emission in the environment. But most of the time, it's also not recycled, and therefore it is wasted into the environment, generating a direct problem to the environment, as you can also see in the picture in the background. Then plastic is mostly fossil fuel based, so this generates even more sustainable problem, let's say. For this reason, there is a need for alternatives, and then this is where upPE-T comes in end. I am not going through this picture because my colleagues already went through the process, so it will be an extra. So, of course, the project is providing an alternative to fossil fuel based plastic, which is the PHBB, and it can also, of course, tackle another problem, which is the plastic waste. So we are not only avoiding the use of fossil fuel based plastic, but we are also using something that is abundant and is a waste, basically. But there is a question that arises. These bioplastics, because the PHBB is a bioplastics, is actually a greener alternative? Is it sustainable? Well, first of all, we have to define what is a bioplastic. Bioplastic can be something that is bio-based, so coming from bio-based material, and it can be biodegradable. There is not a established definition. It's very wide. There is no structured law that establish this definition. So this is very generic, I would say. Then people used to mistake this bio definition with something that is green, it's good for the environment, it's sustainable, but is it really true all the time? Well, this depends on the entire life cycle of this bioplastic. So where the raw material used to produce this bioplastic comes from, or where how it is discarded eventually, how is it biodegradable? Because bioplastic can also not be biodegradable. So it's our end or condition. Then, depending on this life cycle, the results can actually be that the bioplastic can generate actually high emission, or can have land use issues, or using water in a high amount. So overall, it won't be sustainable. But how do we know if the alternatives are sustainable? Specifically, within upPE-T, we are using the life cycle sustainability assessment methodology. And this life cycle sustainability assessment consists of three processes, let's say. First is the three steps, I would say. First is the environmental impacts, which is evaluated via the life cycle assessment. Then there are the economic costs, which are evaluated via the life cycle costing. And then the social impacts of the solution, because sustainability has to be proven in 360 degrees. It's not only about the environment, it's about all the three dimensions. So we go also through the social life cycle assessment. Specifically now, for this presentation, we are referring only to the life cycle assessment, but the challenges are very wide, so can be applicable for to life cycle costing and social life cycle as well. So life cycle assessment is defined by, is standardized by ISO standards, which is the 14040 to 44. And in the ISO, it is established a framework for the life cycle assessment, which consists of 4 steps. The first step is the goal and scope definition of why we are doing this analysis. Then we have the life cycle inventory, which is the data collection phase. Then we have the life cycle impact assessment, in which we define which impact assessment we are using to evaluate our analysis, our data. And then we have the results interpretation phase. However, yes, it comes like a flow, but this is an iterative process, because once we get the results, it is not given that that results are written in the stone. We can change it eventually, going back to the life cycle inventory stage and change some input, because life cycle inventory is a very modular, I would say, based analysis. So the assumptions are not defined by standards. It depends on a single situation. So this can affect directly your results, and therefore you need to go back and then establish a new approach for your analysis. So yes, it's I would say steps, consequent steps, but you can also go back and then get your final analysis. So specifically in upPE-T, our first approach was to evaluate a lab scale amount, which was around 4 grams of PHPV of produced at the time. But this comes with several limitations. First of all, the process was not completed, so we had only a partial analysis. Then we measured high energy consumption, and compared to the amount produced, it was disproportional, and this led to high environmental impact. Then we had the database limitation, because yes, we are using EcoInvent, which is a widely used database, but and it's also quite complete. But if you need some specific inputs that are related to chemical input or anything that can actually be used in upPE-T, because as an innovative process, you can imagine that of course there will be some chemicals adopted within the process. It is possible, it was the case actually, that these inputs were not into the database. So this leads to substitution, or in some case, we could not even consider this input, even if they were relevant amount in the process. So this comes with the first overview of the results. But from this, we understood that we needed to evaluate this the process on a scaled amount. So currently, the lab scale, the pilot scale, is around 4 kg production per week. But we decided to align to competitors and evaluate the sustainability of the production of 400 kg per week of PHBP. This is per week because the process more or less could take this time to complete a one cycle. So the results refers to one cycle, let's say, of production. But this comes with other challenges. First of all, the process is now in a batch mode, meaning that it starts and ends at a specific time. So it's not a continuous process like always running. And so the data that also we got are estimated on an hypothetical 400 kg scenario, based on the pilot scale production, which is the 4 kg production. But this comes with a problem with the results. So yes, we can evaluate the environmental impact in this condition, but this can not reflect the actual impact that the process will have in a real industrial scale production stage. This is because when passing from the batch to other technology, of course, maybe there will be some improvements, and this will lead maybe to also reduction in the impact. So yes, we can get a primary estimation, but can be slightly different from what it will actually be. Then another problem comes practically with the data collection, because of course it's an experimental project. All the steps, all the processes, single processes, were running in different labs all over Europe. And so we got, I would say, fragmented data collection, and then we had to aggregate the data around like a functional unit that is been defined. So also in this case, we had to like go through estimation, and we had to, of course, get the data to complete the analysis. Then another problem that I've already mentioned before is the database limitation. Also in this case, not all the required input were available. And so we had to go on assumption or substitution when it was possible. When it was not possible, unfortunately, we could not include some input into the analysis. So this is an overview of what I just said about the challenges. And from this part of challenges, I would say we could anyway have an estimation of the impact, potential impact of the PHBB production. And this also leads to eventual valorization opportunities and eventually on their impact on the PHBB production. So first of all, I want to give a glimpse of the results that we got, specifically focusing on the hotspot. We identified that because of the high chemical demand for some specific sub-process, this led to high environmental impacts. And so this is also strictly related to what I said before about the valorization activities. But I will go a bit through this valorization in the following slides. Then another hotspot was for sure the energy consumption. Even if in a view of 400 kg production per week, this resulted limited compared to the chemical demand. So yes, it's an hotspot, but it's surely less relevant than the chemical consumption, chemical production actually. But also this leads to high environmental impacts, but this could be tackled by, for example, adopting renewable energy in an industrial hypothetical scenario. So once we have identified this hotspot and then we have all these challenges, what can we do? How can we improve? In a circular point of view, there have been several approaches on reuse resources or to see how these approaches are affecting the overall impacts, and the results are actually promising. As I already anticipated before, now we will go a bit more deep into the valorization activity. So how we can improve this process, how can we improve the impact, reduce actually the impact that we got from this analysis. So these are some of the activities that have been identified, but there are more also under study. So these are just a few of them, I would say, the most relevant. First is the use of the water rejection. This can lead to, first of all, use less water within the process, for sure, but also from reducing the water rejection, we have avoided the emission from wastewater treatments in general. And because of this water rejection contains also some nutrients for the fermentation stages, it's also possible to avoid the use of new resources that leads to avoid to use new production phases for these resources. Then it has been possible to evaluate the use of specific chemicals that were leading to higher environmental impacts. So this, of course, avoid emission from producing a new raw material. And as I mentioned, it reduced the overall process impact. Another valorization is the use of candy waste as a carbon source in general, sugar source or food waste that can be suitable for the production. So this leads to avoid the emission from the production of a virgin carbon source, and this also plus waste valorization activity because we are using something that will be wasted and therefore also avoiding emission from the waste treatment of this waste. So we have a double benefit. In conclusion, we can say that we would not prove that the PHBB is upPE-T is more sustainable than already available recycling technologies or other bioplastic that are still in a lab scale. But because of all these challenges and limitations, but by implementing also these valorization activities, it is proven that the overall environmental impacts will be reduced by significant amounts, and then therefore it can lead actually to a valid sustainable option. So the primary results that we got are actually promising, and with a high margin of improvement in the overall sustainability of this specific production. Thank you. Do you have any question?
Thanks, Maria. Let's see if there are any questions online. No? Okay. We will move on to the last presentation from Maria Nicolas. Maria, if you could just introduce yourself.
Yes, I'm going to share. Okay,
Thank you.
sorry. Mhm. Okay, my name is Maria Nicolas. I work as a R&D project manager in CETEC Biotechnology. And I'm going to talk about the PHB production using Allofresh Mediterranean and the valorization of plastic waste and organic waste. CETEC Biotechnology, well, yes, CETEC Biotechnology or CETBio is a spin-off of the Footwear and Plastic Technology Center of the region of Murcia, and we are specialized in the research and development of biotechnological processes for the production of biopolymer, mainly polyhydroxyalkanoates. So our focus is to transform bioplastic into a sustainable and competitive alternative to conventional plastic through circular economy innovation. Mainly using industrial waste as raw material and employing allophilic microorganisms in the process. In this way, we are participating right now in 5 European projects focused in the PHB optimization and production in a pilot scale. And one of these projects is the upPE-T project, and is the reason why we are talking here about. So first of all, I want to explain what are polyhydroxyalkanoates. I'm pretty sure that most of you know what I'm talking about, but I want to explain that these PHAs are aliphatic polyesters accumulated intracellularly by microorganisms as carbon and energy storage granules under nutrient stress conditions. Mainly when the concentration of carbon are really high and other nutrients are really low, such as nitrogen or phosphorus. These PHAs are fully biodegradable in soil, water, and compost. They are biocompatible, which means that they can also be used in biomedical applications. And they are thermoplastic with a high versatility in processing. Their properties range from rigid to elastic depending on the monomer compositions. We can say that we can classify these PHAs into two main groups, the short chain length PHAs and the medium chain length PHAs, depending on the length of the chain. We can also say that between these two groups, the PHAs can be composed of one or two or more monomers. Here we will be talking about the PHBB, which is a short chain PHA composed of two different monomers. But the PHB, which is a short chain PHA and homopolymer, is the most studied PHA. It is rigid, but it is rigid and crystalline. As applications, the PHAs can be applied in multiple industries. They can be used for bio-based packaging, for medical devices and drug delivery, for the production of agricultural films and coatings, and also in cosmetics for the production of biodegradable microbeads. Regarding the PHCB, which is the biopolymer that we are trying to optimize its production, it is composed of two different monomers, the hydroxybutyrate and the hydroxyvalerate. It is also a biocompatible and biodegradable polyesters, which can be produced by different species of microorganisms. We are using an allophilic archaeon, but it can also be produced by other bacteria. And what makes this biopolymer interesting is the presence of the hydroxyvalerate monomer, which can reduce the crystallinity, making the polymer more flexible and less brittle than the PHB. And so improving the mechanical properties and also lowering the melting point. In the upPE-T project, from the whole value chain from the project, ZBio is the responsible for optimizing and scale up the fermentation process to produce the PHBB in various grades for bio-based and biodegradable food and drink packaging, utilizing PET degradation products and other organic waste as feedstock. And why we are using these wastes? Well, I wanted to highlight that every year in the European Union, we produce more than 100 million tons of bio-waste. And from these million tons, the 40% is landfilled, which cause great emissions of greenhouse gases and the pollution of soil and groundwater. And also talking about the plastic waste, we generate annually in the European Union about 16 million tons of plastic waste, and only 6 million tons are currently recycled, which means that the other 10 million tons of plastic waste are landfilled or incinerated in our ecosystem, and they can accumulate in this ecosystem, causing major environmental problems such as the microplastic formation, the pollution of soils, water, food, and also causing great greenhouses gases emissions. So here in the project, we are trying to give an alternative of management of this kind of residues by incorporating in biotechnological processes for the production of the biopolymer PHBB. So in the upPE-T project, we have developed the holistic approach to produce the PHEV from this kind of residues. So we have developed an innovative systems that combines two microbial species to repurpose plastic and organic waste into PHEV. As my colleague Friedman from Enzymical has explained before, they are degrading the PET bottles through enzymatic hydrolysis. So what we are doing is use the mix of the P degradation byproducts to feed Cumamonas testosterone, which is a strain able to metabolize the TPA and to produce biomass that can be further used in Aloferas mediterranean fermentation for the production of the PHBB, which is later transformed in bioplastic for different packaging applications. So from the PET degradation byproducts, we can obtain ethylene. Well, the holistic approach is a two-step process. From the PET enzymatic hydrolysis, we can obtain two monomers, the ethylene glycol and the terephthalic acid. This ethylene glycol could be repolymerized for PET manufacturing or for other industrial processes. Could also be valorized in biotechnology as carbon source, but in our process is toxic for Cumamonas testosterone growth in concentrations higher than 2 grams per liter, which is the maximum concentration that we can feed our microorganism. On the other hand, the terephthalic acid, the TPA monomers are reproductive toxicants, and they are very difficult to upcycle due to their stable aromatic ring. And if it can be correctly purified, they can be also repolymerized for PET manufacturing. And we can also metabolize this monomer by Cumamonas testosterone. And this is what we have developed in the upPET project. So from the whole mix of the enzymatic hydrolysis of PET, we feed with all these meats containing ethylene glycol and terephthalic acid without any purification. We use this mix to feed Cumamonas testosterone and for the production of a biomass rich in nutrients for Aloferas mediterranean PHBB production process. So with this approach, we reduce the purification needs of the monomers, and we can give other high value other high value application for these monomers. So how we can metabolize this TPA, how can Cumamonas testosterone use this mix of PET degradation byproducts? Well, Cumamonas testosterone is a gram-negative beta proteobacteria. It can be found in soil, wastewater, and sediments, where it plays a crucial role in the biodegradation of persistent chemicals such as aromatic compounds. It is able to degrade and assimilate phthalates and aromatic hydrocarbons, and this is the reason we are using this strain for the metabolization of the TPA. How can Cumamonas testosterone metabolize the TPA? Well, through several steps or enzymatic degradation, the TPA is transformed into pyruvate by Cumamonas testosterone, and the pyruvate enters the 3-carboxylic acid cycles. And during these cycles, as some of you know, Cumamonas testosterone produce energy for biomass growth, as well as many other microorganisms. So from the metabolization of the TPA, we were able to produce 1 gram per liter of common monas biomass, common monas testosterone biomass, with a maximum concentration of TPA metabolized of 4 grams per liter. The second step consists on the use of this common monas testosterone biomass as a part of the culture medium for the Allophorus mediterranean fermentation and the production of PHBV. So for the production of PHBV, we are using Allophorus mediterranean, which is an allophile archaeon, which requires a high salt concentration for survival, which is toxic for other microorganisms. So this has two main advantages. Because we can reduce the sterilization requirements, so we can work in other bioreactor and not in the still ones. So this is the reason, because we have designed and installed our own plastic bioreactors and not still ones, reducing in this way the equipment cost and later the energy cost, because we don't have to sterilize the culture medium to work and produce the PHBV. This microorganism is also capable of accumulating this kind of biopolymer with a molar content of hydroxyvalerate of 10% without precursor addition, but we can also modulate and increase the hydroxyvalerate molar content, adding some volatile fatty acids to obtain a PHBV with a hydroxyvalerate content of 30% or more than 30%, as we have obtained in the upPE-T project. And it is also a microorganism with a high versatile metabolism, which allow us to feed them with several wastes, such as organic wastes or which contains nutrients to feed them, so we can change commercial substrates with these wastes and also reduce the cost of the overall process of PHBV production. So the process consists on the PHBV production with Allophorus mediterranean, using common monas testosterone biomass as a nutrient-rich substrate, also using confectionery waste as carbon source, and also with the addition of hydroxyvalerate precursors to increase the concentration of the hydroxyvalerate and make the polymer more flexible and with better mechanical properties. So we have optimized the whole process for the production of PHBV, considering the physicochemical parameters such as the pH, the temperature, the concentration of salts. As I said before, we have worked with a allophilic microorganism, so we need a high concentration of salts of around 20%. So we have optimized the whole process considering the physical conditions and also the nutrient condition to be able to add this kind of wastes in order to replace the commercial substrate. So from the whole process, we have been able to optimize to obtain a PHBV yield of around 2 and 3 grams per liter with a concentration of hydroxyvalerate of around 30%. So in a step forward, further than upPE-T project, we are now working in the construction and installation of a pilot plant for the production of PHBV in almost 2,000 liters in order to scale up our process and do more experiment and more trial and have more material to study the characteristics and mechanical properties also. So we have built bioreactor plants based on plastic bioreactors, fully controlling the temperature, pH, stirring, dissolved oxygen. After this fermentation stage, we are applying a tangential filtration in order to concentrate this biomass, which has the PHBV inside the cells, and concentrate the biomass to further dry in by evaporation. So we have also installed evaporation to dry the biomass and also to dry the brine and can and be able to recirculate the salts that we are using in the fermentation process. After that, after the drying of the biomass, we are also extracting the PHB using a pilot Soxhlet equipment with a green solvent. And after all these processes, we have been able to produce these lollipop sticks and packaging material, as my colleagues before have explained, Alejandro and Mariana. And finally, I want to highlight these takeaways for the production of the PHCV. We can say that the PET and biowaste are major environmental challenges, but also opportunities for innovation in circular economy approaches. That the biotechnological solutions like those developed in that project can turn packaging and organic waste into valuable resources using specialized microorganisms such as Coamonas testosterone and Allophorus mediterranei. And this one, Allophorus mediterranei, can offer powerful tools for sustainable PHBV production, because it is a very promising biopolymer with renewable origin and fully biodegradable. And however, its higher production cost also remains a barrier, but we can combine this biotech innovation with circular economy strategies to be able to implement this kind of production. So that's all from my side. Thank you very much for your attention. If you have any question, I will be happy to answer.
Thank you, Maria. Let's see if we have any questions. If not, I will, and before we go, I will ask Fuensanta to summarize or wrap up of our today's final webinar for upPE-T.
Yes, well, as a summary, in upPE-T, as Friedemann and Maria explained, we've been able to develop a technology based on biotechnological routes to transform fossil-based plastic waste into a biodegradable plastic waste. And we have also able to validate this new formulation and new plastic packaging with the end users in industrial environment. But an important part, apart from developing this new technology, has been identifying important challenges, such as putting these new products and processes into the market. For that reason, we have also worked on elaborating the innovation, the exploitation, and the business plan with the strategies, important strategies to put everything into the market. And also we have identified important hotspots regarding environmental impact or economical feasibility, thanks to the working on the life cycle assessment, but also using waste as secondary raw material in the different processes, and of course proposing solutions for byproducts, the byproducts that are generated in the different processes. So, well, we've tackled the whole important aspect of the solution, upPE solution, in the technological point of view, but also environmental and economical, and scaling up, putting into the market point of view. And thank you to the speakers for these interesting presentations.
Very interesting
And thank you
presentation.
to you, Angela, for organizing the webinar.
Thank you very much. Thanks everyone for keeping it on time. It's our final webinar, a final event for the upPE project, as it's coming to an end in the end of April. I just wanted to thank everyone, and I will say that the recording of today's webinar will be available on our YouTube channel, and we will share it on social media and on our website. Until we meet next, thanks for attending and for participating today. Thank you all.
Thank you all.
Thank you.
Thank
Bye.
you.
Bye. Bye.
Thank you.
Bye.